Hi, this is Kumar Singh from Designed Analytics LLC, and you're watching another episode of Throwback Thursdays or Thursday Throwback. It doesn't matter, right? Because the gist will remain the same. Well, so the research paper that we are going to discuss today is this specific research paper, right? Random forest. And before we get into the research paper, I think it's kind of critical to understand the context, right? And then we get into the details of the research paper. So we try to understand why random forest, the concept that was postulated in this research paper, why is it important, right? So before we get into the topic of random forest, there are a few key aspects that we want to kind of get into. The very first one is the way I pronounce it is ensemble machine learning method, right? Depending on what part of the world you are, what kind of English accent you have, what kind of pronunciation you have, some may call it ensemble, I call it ensemble. But what is that method, right, in the context of machine learning? An ensemble method is basically several weak learners when they are combined to form one strong learner, right? Or essentially an amalgamation or combination of different methods of machine learning. So you have to kind of remember, when I say weak learner, I mean a weak model, right? Because the concept of ensemble and then the subsequent term of bagging that we are going to discuss is generally mentioned or like discussed upon in terms of weak learner and strong learner. So I'm using that language, but it's essentially a weak learner is a weak machine learning model that's not that great at learning. I mean, a simple way to put it, right? So ensemble methods are basically a combination of, it could be same combination of multiple models of the same type. Sometimes it may be a combination of different types of machine learning models, right? So one of the categories of ensemble methods is bagging, or one of the approaches, you can say, right? How does that work, bagging, right? So you have, say, an original data set with ensamples, right? So you do a bootstrap sampling. So what basically you do is, instead of training just one model, you create multiple bootstrap samples by randomly drawing ensamples with replacement from the original data set, right? Each bootstrap sample will look slightly different. Some points may repeat, others may be left out, right? And then you train multiple models. So you train a separate model, which is often a decision tree, on each bootstrap sample that you took, right? And because the samples differ, each model will learn slightly different patterns, right? What do you do next? You can actually imagine what will you do next. You will aggregate the predictions, right? So for classification, each model votes on the predicted class and the majority vote is the final prediction. And for regression, you take the average of all model predictions, right? Now, why does it work, right? Why, if we combine like different weak learning decision trees, for example, why will it give a strong learner, right? Well, there are few reasons that we can touch upon. It reduces variance, right? So combining many weakly correlated models makes the final output more stable than any single model, right? It leads to less overfitting, right? So individual decision trees might overfit, but averaging across many reduces the risk. Built-in validations, right? So samples which are left out of each bootstrap, called out-of-bag samples, can be used to estimate accuracy, right? Without needing a separate validation set. So where does then the random forest fit in? And why did we cover bagging? Like, we started with ensemble, then we covered bagging. Why did we cover it? Because bagging is the foundation, right? Random forest actually builds directly on bagging. So we still take multiple bootstrap samples like we just discussed, right? Random samples with replacement from the data set, right? We then train many decision trees, right? So, or you can say we still train many decision trees just like we did in bagging. We still combine the predictions actually, majority vote for classification, average for regression, right? The key twist here is the random feature selection. So when each tree is built, at every split in the decision tree, instead of considering all features to choose the best split, right, the algorithm considers only a random subset of features. So for example, classification, right, the forest trees tend to be more diverse, right, and less correlated. I think it will hold for regression as well, right? Then you train the forest, so which is basically repeat the process to grow hundreds of thousands of trees. And each tree is different because of both the random data sample from bootstrapping and the random feature subsets at each split. And then you do the prediction, classification, each tree votes, and the majority class is the final output. For regression, each tree outputs a value and the forest averages them. Why does random sampling work? Well, it reduces correlation. Random feature selection, like we mentioned, ensures trees aren't all making the same mistake, right? Variance reduction, averaging many diverse trees leads to more stable predictions. Good accuracy plus robustness, right? Handles large data sets and noisy features very well. And feature importance. Random forest can measure which variables are most useful for prediction. For example, by tracking how much each feature decreases node impurity or permuting features to see the impact. So in short, the reason we started with bagging was because random forest equals bagging plus random feature selection, right? So essentially it grows many decision trees on bootstrap data subsets, splits each tree using only random feature subsets, and combines the results. And this extra randomness makes the ensemble stronger, less correlated, and highly accurate. And that is why this paper was an instant hit, was adopted largely and profusely, and it ended up becoming one of the very important ensemble machine learning methods, right? So coming back to the paper, what was the core innovation in the paper, right? Well, the paper, I think the author was Leo Bremen, if I got the author right. So what were the core innovations in the paper? Well, we know we have already discussed a little bit about random forest already. So random forest was a proposition in the paper, an ensemble learning method that combines many decision tree classifiers. Each tree is trained on a randomized version of the data and contributes one vote towards the final prediction, majority vote for clarification, and average for regression, as we just discussed, right? And Bremen expanded on the concept of bagging, like we just discussed, right? And the random subspace method, selecting random subsets of features at each split to grow strong, decorrelated trees, right? In terms of theoretical insights, the two key ones are convergence and overfitting. As the number of tree grows, the generalization error converges and overfitting is not a concern, as you can assume, right? The model remains stable with enough trees. Error bound. So the algorithm's accuracy hinges on two factors: the strength of individual trees, which is each tree's predictive accuracy, and the correlation among trees. And low correlation and high individual strength lead to superior overall performance, as you can imagine. Another key area because of which this method kind of gained prominence was practical mechanics, right? So bootstrap sampling, bagging, where each tree is trained on a bootstrap sample, right? Random sampling introduces diversity among trees, reduces variance. There was this feature randomness we already discussed. At each node split, a random subset of features is considered, and that further reduced correlation between the trees and improved the robustness of this ensemble method. Out of bag error estimates, since each tree is trained on only part of the data, the remaining data, and I think we discussed that before, serves as a built-in validation set, right? Allowing for unbiased estimation of performance during training, variable importance, because the method quantifies how much each feature contributes to prediction accuracy, often via permutation importance or decrease in impurity, providing interpretable insights, right, into the model's reasoning. So, what were the key advantages then of this approach? High accuracy and stability, superior predictive performance compared to single decision trees, and it's very resistant to overfitting. We have mentioned or touched upon that many times now. Scalability, handles large data sets and high dimensional feature spaces very efficiently. Robustness to missing data and outliers, maintains accuracy even when data is incomplete or noisy. Feature important insights, right? Importance insights, sorry. Enables feature rankings, right? Aids in variable selection and interpretation. So, to summarize, this paper from Leo Bremen blended bagging and random feature selection into a robust ensemble method, and that method remains a staple in modern machine learning, valued for its balance of accuracy, interpretability, and resilience against overfitting. Thanks for watching. I'll see you again next week.